All right, in our previous video, we were deriving velocity equations for Sally. So velocity of Sally is equal to negative 5 multiplied by our vector hat I plus 5 multiplied by our vector hat j. And the velocity of Kelvin, that one was equal to I minus 2t multiplied by vector hat j. So the question we had is at time equaling 1 second. So we're going to plug in time equal 1 second to both functions here. And we find out that the velocity of Sally, of course, that's going to be equal to a negative 5I plus a 5j, because we can't plug anything in for that at all. And the velocity of Kelvin is going to equal I minus 2. And multiply that by vector j. So that's the velocity equations for both of them. Now remember, these are their x and y components. So if we want to figure out, okay, what the angle is between them, then we need to use the tangent function to find what angles they're at. So I'll take the tangent of theta here. Okay, and I'll set that equal to, of course, we have what, a 5 over a negative 5. So 5, and I'll just keep them as absolute values right now. 5 over 5, that's 45 degrees. Now, of course, a negative x and a positive y, that means north of west. Okay, let's do likewise for Kelvin. The tangent of theta is going to equal 2 over 1. Okay, and that equals 63.4 degrees. Now we have a negative y and a positive x. That'll be south of east. Okay, so that's our approach for that. Nothing too hard. Well, then the question actually was, what is the actual value between these two vectors? So if we just do a brief sketch here, I'll just draw dotted lines for our x, y. Let's see, our north of west vector is pointing this way, and of course we have another one pointing downwards like this, and this will be the angle between them. Okay, so we've got 90 plus a 45 here, plus whatever angle we've got here. So let's reference that. We've got this angle here referenced. We have this angle referenced. So what we got to do is this angle plus this angle here, but we need this one here. So I got to take 90 minus this to get this piece here. So getting the angle between them is going to be 90 plus 45 plus a parenthesis 90 minus 63.4. And that comes out to be the 3 significant digits, 162 degrees, okay, between those two angles there. Now we could also use the dot product to solve for this. I do find that a little bit more challenging to do, but it would be helpful for us if we know that method too. So I'm going to go through that right now. Okay. Now, if we have two vectors that we wish to cross product, we need to remember how to do that. So if I have A times our vector unit 1 there for I plus B times J. Now, A and B are just constants multiplied in front of those guys, or they could be functions. It doesn't matter. Let me do a dot product, okay, with another vector C I plus D J. Okay, that's it's actually going to come out to be a number, and it's a scalar quantity, and we're ending up with, and I'm going to multiply my two I coefficients, so it'd be A times C plus my two J coefficients, that'd be B times D. And that's actually how we do that. Okay, but there's also another way of doing a vector cross product. I'm going to take the magnitude of vector A, and we'll call this one vector A here, and this one vector B. So A dot B, okay, is equal to the magnitude of A multiplied by B times the cosine of theta. So if I want to take two vectors and dot product them, this is also another way of doing it. You might have done in the past work as force times distance, cosine theta. So that's an example of how to do that. Okay, well, let's get the magnitude. Okay, and there's another way of representing magnitude, just to let you know. We can write the vector like this and then do double bars on either side. That means magnitude. I use capital letters in this example, which is sometimes also used. Okay, so let's get the value, okay, of the velocity vector of Kelvin. Okay, that'll equal 1 squared plus, okay, and I believe that should be a 2 squared. Okay, but in the case it was negative, so we can keep it negative 2 squared. And that's all under a square root. Okay, and that comes out to be equal to the square root of 5. And sometimes I don't write my negatives in there because I know I'm going to square them anyways. Okay, now what about the velocity of Sally? Okay, let's go ahead and do that. That's going to equal then the square root of negative 5 squared. Okay, plus a positive 5 squared, which then equals the square root of 50. Okay, so that's how we're going to do that. Now, why do we do that? Well, because we've got two different ways we can do this. So we've got the value of A times B, okay, times the cosine of theta, okay, does equal A dot C plus B times D. Okay, because we said this is a vector dot product, and that's what that equals. And this, of course, is also a vector dot product, and so is that. So we set the two equal to each other. Okay, so to figure out our angle then, well, we know the value of our two vectors here. Okay, so I'm going to take the square root of 5, okay, multiplied by the square root of 50. Equals. Okay, now we need to do the vector dot product, okay, for our previous example there, right? Okay, so I'm going to do that over here, and then we'll place that number there. So let's go back to our vector. Okay, our vector is I minus 2j, and we need to dot product that with a negative 5i plus a 5j. And I'm kind of running out of room. I'm smashing that there a little bit. Okay, so let's go ahead and do that then. So I'm going to take this coefficient and multiply it by that one. So that's going to be a negative 5, because 1 times a negative 5 is a negative 5, plus, let's take our negative 2 and multiply it by a positive 5 plus a negative 10. Okay, which is going to equal negative 15. Okay, so let me rewrite this because I forgot my cosine of theta there. So we're going to take the square root of 5 multiplied by the square root of 50. And then we're going to say times the cosine of theta is equal to a negative 15. And yet with theta is equal to 162 degrees. Okay, just like what we did before. And like I said, I find this way a lot more challenging, but at least you can see how our vector properties are applied. In our final video, we've got one more example, okay, for two-dimensional motion before we go on to projectile motion.